Okay, so previously we were looking at say systems of equations. So this is system with three equations and three unknowns x1, x2, and x3. And what we looked at was solving something like this using equation operations, right? Okay, so we had three types of equation operations. The one that we tend to use probably the most is when you add a multiple of one equation to the next equation. Right, so we did this example already very quickly. Okay, so the idea over here is if you have this system of equations, right? One way to do it using these equation operations is use your equation operations to get it in a form like this over here, which is essentially say upper triangular on this left hand side. And then once you have that, what you can do is you can back substitute, right? So this x3 is equal to 4, you put it in and you solve it and you get x2 is equal to minus 3 and so on. You can get x1 is equal to 2 when you substitute x2 and x3 into this over here, the first equation. Okay, so the point of your equation operations is to get down to something that is triangular like this on the right hand side, right? And then it's easy to solve, right? You may not always be able to do this, right, to get it nice and clean like this, and you're gonna see that for different cases. All right. So the equation operations, well, the equation operation that I use here is okay. So given this first equation, what I want to do is I want to get rid of this x1 over here, and I want to get rid of this 2x1 over here, right? So I get rid of this first x1 over here by multiplying this equation by minus 1 and adding it to equation 2, right? So minus 1 times equation 1 and I added to equation 2, so minus over here plus this would give me 0, minus 2 plus 3 would give me 1, minus 2 plus the 3 would give me 1, and minus 4 plus the 5 would give me 1. So that's how I get this, right? And similarly, I will get rid of this 0 over here by multiplying this equation by minus 2 and adding it to this one, right? Okay, and I keep going like that, right? Until I get this triangular form, right? Okay, so we talked about that last time. Okay, so what I also mentioned last time is that, okay, so for example, if I go from this system over here to this system over here, right? What I'm doing is I want to make this 2 over here 0, right? And I multiply this equation by minus 2 and add it to this one here, right? Okay, now when I do that and I multiply this by minus 2 and add to this, right? I'll have minus 2 over here times the 1 added to this, which would be give me a 0, minus 2 times this 2 over here, which would give me minus 4, plus this 6 here would give me 2, right? Minus 2 times this 2, which is minus 4, plus this 5, which would give me 1. And then minus 2 plus this, minus 2 times 4, which is 8, plus 6 would give me this minus 2, right? So that's how I get the 2, 1, and minus 2 over here, right? And you want to notice I didn't really do anything with the x1s over here, right? So this x1 and the x2 and the x3, they just remain where they are, and just the coefficient in front of them that is changing, right? And the constant term is changing, right? So this notation is a little bit cumbersome, and what you can do is you could actually just drop off the variables over here, right? Provided you do it in a systematic fashion, right? Okay, so so how do you drop off the variables and so, right? So this is same system. The system over here is the same as the system over here, right? Okay, so what you're doing is that what you're doing is you have your system over here, right? and you really want to record these coefficients in front of them in a systematic way, right? Okay, so for a system over here, what you do is you form something called an augmented matrix, right? Right, on your left hand side over here, so you have this vertical line here, right? On the left hand side over here, these are the coefficients coming from the equations, right? So okay, so over here the coefficient of the x1 is 1, coefficient of the x2 is 2, and this is 2 over here, so I get 1, 2, 2 here, right? Likewise over here I have 1, 3, 3, so I get the 1, 3, 3, and so on, right? And notice also, okay, so for the first equation I have 1, 2, 2, and then the constant term, which is 4, comes across on the side, right? Okay, so your system over here, you write it in this augmented matrix form, right? And what you're doing is you're just recording the information about the system in, well, a kind of a consistent way, right? Right. Okay, so what I mentioned was what you want to do is you want to start right, so when I do my equation operations over here, right? So for example, going from this system over here to this system over here, right? What I did is I did this equation operation, right? Minus 2 times this equation and added to the third equation, right? Okay, so just use the exact, well, the corresponding operation, right? Okay, so what I said, I guess previously also, was that you don't really need to write down the x1s, the x2s, and the x3s, right? What you could do is you could just keep track of these values over here, right? All right, so if I want to go from here to here, right, all I need to do is just modify the values, right? Okay, so this one over here is equal to this one, right? And what I'm doing is I'm adding, gonna multiply, gonna do this equation operation. So I'm gonna multiply this by minus 2 and add it to this, right? Okay, and what you're doing is you're just multiplying the coefficients over here by minus 2 and you're adding it to your third equation, right? And notice when you go from here to here, right, that is what you're doing, right? So going from here to here, this notation over here, minus 2 times row 1 plus row 3, means for this matrix on top, right, what I do is I multiply by minus 2, right, and then add to the third row, right? I don't actually change the row 1, right? So this is the row operation that I'm going to do, right? Minus 2 times row 1 plus row 3. Multiply over here throughout by minus 2, right? Minus 2, right? Times the 1 plus the 2 would give me 0. Minus 2 times the 2 would give me minus 4 plus the 6 would give me 2. Minus 2 times the 2 would give me minus 4 plus the 5 would give me 1. And minus 2 times the 4 would give me minus 8 plus the 6 would give me minus 2, right? And that is actually exactly what I did when I went from here to here. Not exactly, I mean over here you had the x1s, the x2s, and the x3s, right? As I said before, you don't really need them, right? Once you keep track of the numbers in a systematic way, right? Okay, so I mean this is the approach that people normally use over here, right? What you would do is you would have your system to start off with, right? And then you record the numbers in a augmented matrix, so that is keeping track of the coefficients over here. And these equation operations, for example, to go from here to here, right? To go from over here to here, right? To do the equation operations, what you do is you just work on the coefficients, and working on the coefficients, you're doing it via row operations, right? Okay, so next thing you want to note over here, this is going from this system here to this system over here, right? What you're doing is you're multiplying equation 1 by minus 2 and adding it to equation 3, right? Okay, and over here, going from here to here, you're multiplying row 1 by minus 2 and adding it to row 3, right? So this row operation over here, this minus 2 row 1 plus row 3, right, is corresponding to this equation operation over here, right? Okay, so remember when we're doing this over here and we no longer writing down the x1s and the x2s and so on, right? All you have is just rows and matrices, right? Okay, so while you're basically doing the same thing. You want to be consistent with the notation that you had previously. You want to be consistent with the equation operation notation. So you use a new notation over here, but this notation over here, if you're thinking of it in terms of the system, right, going from this system to this system, it actually means basically the same thing, right? Okay, right. So your equation operations. For example, this equation operation minus 2 times equation 1 plus equation 3 corresponds to this row operation over here, right? Okay, and if you want a next example of this, right, so when I got this system over here, right, in order to simplify, what I needed to do is get rid of this 2x2 over here, right? So I wanted to make this 0, right? Okay, so what I do is multiply equation 2 by minus 2 and add it to equation 3, in which case I will get a 0 over here, right? Alright, so likewise over here, what you have is you have the 1 and the 2, right? Like the 1 and the 2 over there, the 1 and the 2, right? And what you want to do is you want to make this 0 here, right? Now how do you make it 0? What you do is you multiply your row 2 by minus 2, right? Now this notation over here means that you're referring to the matrix above, right? Okay, so minus 2 times row 2 would give me a minus 2 over here, a minus 2 over here, a minus 2 over there. And when I add it, I'm going to get 0 here. I'm going to get minus 1 over here. And I'm going to get minus 4, which is the same thing I got when I went from here to here, right? Okay, so this this row operation over here, right, corresponds to this equation operator over here, right? Okay, so your equation operations have corresponding row operations, right? Okay, and eventually what we're going to do is we're not going to use equation operations. I'd expect you to be able to do these and to remember the notation, right? But most of the times we will be using the row operations over here, right? We just saw an example where the equation operations would correspond to row operations, right? Okay, so let's look at the definitions, right? We did this definition previously, right? You have 3 types of equation operations, where one type is you could swap 2 equations. Next one is multiply throughout by a non-zero scalar, and then the third one is you add a multiple of one equation to the next equation, right? Okay, so because the equation operations correspond to the row operations, right, you'd expect to have the same type of row operations, which we do, right? So the row operations that we have, it's going to swap the location of 2 rows, okay, and that corresponds to swapping 2 equations. You could multiply each entry of the row by non-zero scalar, right? And that corresponds to number 2 over here, right? Where you multiply each term in equation by a non-zero quantity, right? Okay, and then this third one over here, adding a multiple of one equation to a second equation, that corresponds to adding a multiple of one row to an next row. Okay, all right. So the notation that we will use, right, that I use in these notes is if you're going to swap 2 rows, it's row I exchange with row j, right? So you have this arrow on both sides here, this line, right? So row I exchange with row j, right? Right, this one over here this means just multiply row I by a scalar, right? And you want to make sure that this scalar is non-zero, right? If you multiply by a zero scalar, that will affect your solutions, right? So it's not good to multiply by a zero scalar here, right? Scalar here must be non-zero, right? Okay, so this last notation over here, right? Okay, so the notation that I will use in the notes here, this is you add in a multiple of row I, right? So you're multiplying row I by a scalar and add into row j, right? Okay, so this over here, you just need to be a little careful about how you interpret it, right? Right. Well, which one is actually changing? Is it the row I or is it the row j, right? And how we write this over here, it is the last one here, right, is the one that changes, right? Okay, so whatever row it is in this second position of your sum over here, this is the one that changes over here, right? Okay, so let's look at some simple examples of these three types of row operations, right? Okay, so this is an example later on in the notes, but we're just going to focus on the row operation aspect of it, right? Alright, so this is some matrix over here, right? Now you can apply your row operations to any matrix, right? The matrix does not need to be an augmented matrix, right? Okay, so any matrix you can apply these row operations to, right? Right. Okay, so let's do an example of row exchange in two rows, right? So here, what I have is I have this matrix to start off with, and what I'm going to do is I want to exchange these two rows, row 1 and row 2, right? So going from here to here, you notice that, well, second row is now in the first position, first row position, and the first row over here is now the second row over here, right? So going from here to here, right, what you did is you switch row 1 and row 2, right? This second arrow over there, you don't really need that second arrow, right? Really all you need is just this line over here, row 1 exchange with row 2, right? Okay, so row 1 exchange with row 2 means that when you went from here to here, the end result is that you switch these two rows, right? Okay, what this one over here is c times row I means you're multiplying row I by a non-zero scalar, right? Okay, so going from here to here, right? Let's forget about the circles over here for the time being, right? What you have is you have this second row over here, and the second row, what I want to do is I'm gonna multiply throughout by 1/7, right? So going from here to here, when I multiply throughout by 1/7, I know this is only the second row that is changing. So I'm multiplying by 1/7 is the same as dividing by 7. So I'm gonna get a 1 here, minus 3 here, and a 9 on 7 over here, right? So that's multiplying this second row by scalar 1 on 7, right? So you go from here, and this is where the end result is, right? Okay. All right, and then an example of multiplying row I by a scalar and adding it to row j, right? Okay, so let's go in from here to here, right? Okay, so what I want to do is I want to multiply this row by minus 2, add it to this row, right? And it's going to be this row, the third row that's going to change, right? When I multiply this by minus 2 over here, I'm not actually changing it over here. Multiplying by minus 2, you can think of it as some kind of buffer or something like that. Multiply by minus 2 and you add it to this, right? Okay, so multiply over here throughout by minus 2. I'm going to have minus 2 over here plus this 2 will give me 0. Minus 2 plus this would give me minus 1. Minus 4 times 4, which would be minus 8 plus 7 would give me minus 1. Minus 2 times minus 5 is 10, plus the minus 7 is 3, and then minus 2 times this minus 2 times the 2 is minus 4, and added to the 2 gives me minus 2, right? Okay, so you get this over here, right? So going from here to here, you add minus 2 times row 1 to row 3, right? This row 3. Okay, and this is the end result, right? And notice the notation is it's the row 3 that actually changed, right? The row 3 changed from here to here, not the row 1, right? The row 1 remained the same. Okay, so we now have this definition that if I have two matrices of the same size, right, they call row equivalent if you can go from one to the next one by a sequence of row operations, right? Okay, so for example, this matrix over here, this A is row equivalent to B over here, right? Okay, so how can you go from A? Well, if they row equivalent, it means that you must have a sequence of row operations, possibly one, possibly two, possibly three, or so on, some finite number of row operations that will take you from this one to this one, right? And in this case, if you multiply a second row over here by -2 and you add it to this, right, then you will get this matrix here, right? And then when you multiply this third row over here by -1, right, you'll get this row over here, right? And so notice those two row operations take you from this matrix to this matrix by an intermediate matrix in the middle, right? But you did go from one matrix to the next matrix by a sequence of row operations. So matrices A and B are row equivalent, right? Okay, if you want a next example of this over here, right? If you say you consider this matrix here, right, that I have, right? What I'm doing in this problem is I'm applying a sequence of row operations. So to go from here to here, I do this row operation. To go from here to here, I do this row operation. And then I keep doing row operations, right? So I get from this one here, this A over here, to this one over here, right, by a sequence of row operations. So what that means is that, well, that's an example of this matrix here being row equivalent to this matrix over here. So let's recall what it means for two linear systems to be equivalent, right? Okay, so two linear systems are systems of linear equations equivalent if they have the same solution set, right? Okay, so for example, if you look at this simple 2 by 2 system over here and you look at this simple 2 by 2 system here, right? Well, how you go from this system here to this system over here is you just multiply equation 2 throughout by 2, right? And that doesn't change the solution set, right? Okay, so it's pretty easy to check to see, and we did this previously, right? That solution set over here is the same as the solution set over here, right? So these systems are what you call equivalent, right? And if you want a next example of that, right, this system that we did in a previous lecture, and we just talked about actually. So this system over here, we do some equation operations to it, and we get this system. And the point about the equation operations is that they don't change the solution set, right? So we did this in a previous lecture, right? So when we do an equation operation, we don't change the solutions, right? Which means that when I go from here to here, solution is the same when I go from here to here, and so on until I come down to here. And the point is that the solution set for this is equal to the solution set for this, and this one is easy to get the solution set, right? It's easy to get it from here by back substituting, and because it's the same solution set here, it means that we solve the system, right? Anyway, so equivalence mean systems being equivalent mean that they have the same solution set. Okay. All right. Okay. And now what I want to do is I want to discuss this theorem over here, right? Okay. So we talked about row equivalence, right? Two matrices are row equivalent if you have a sequence of row operations taking you from one to the next one. We just talk about equivalent, right? Okay, so you have row equivalent matrices here, right? And then you have a next notion, which is equivalent systems, right? And what this says is that row equivalent matrices represent equivalent systems, right? Okay, so what does that mean? Let's look at an example here. Right. Okay, so this is a system over here, right? right? This is a system over here, and this is the augmented matrix that represents it, right? Okay, so augmented matrix over here represents this system, right? Now, what we do is we talked about this, right? What you could do is you could apply row operations to this. You apply row operations to this until you get it in this sort of a triangular form, right? Well, we didn't quite talk about this because this process over here is part of a Gauss-Jordan algorithm, right? But you can do apply row operations to this augmented matrix until you get this one over here, which has this sort of triangular form, right? Anyway, the point is I have system over here to start off with, and it has an associated augmented matrix. Right? And now what I do is I apply row operations to this augmented matrix, and applying row operations to these matrices means that this one is row equivalent to this one. Likewise, this one over here is row equivalent to this one, right? And similarly, this one, this last one here, is row equivalent to this, right? Okay, why is it row equivalent? Because you can go from here to here by a sequence of row operations. All right. Okay, so this is an augmented matrix here, right? And this is, so it's the same, this matrix here and this matrix here, right? They're row equivalent, right? This one represents this system, this linear system, right? So this is the augmented matrix for this linear system. So that is what I mean by represents, right? Your row equivalent, this matrix over here represents the system. This matrix over here represents the system, right? And the point is that these two are row equivalent, right? These two are row equivalent, right? And because they're row equivalent according to this theorem, what that means is that the systems that they represent, right? So this one represents the system, and this one represents the system. These systems, okay, so row equivalent matrices, this and this are row equivalent, and the systems that they represent, right? Those are equivalent, right? Okay, so this represents the system, this represents the system, and the systems themselves are equivalent. In other words, they have the same solution space, right? Okay. All right, so why would you care about something like this? Well, why you care about something like this is you start off with a system over here, right? And then you're going to form your matrix, augmented matrix. And then what you want to do is you want to simplify this until you get your triangular form, right? Right. This is the same as doing equation operations, as I mentioned, right? To get the system in a nice form, but what you're doing is you're not keeping track of the x's, right? Okay, so you have your system over here. Form your augmented matrix. Apply your row operations until you get something that is roughly triangular, if you can, right? And then form your corresponding system, right? And what this is saying is that just this system that you form over here is basically the same thing as the system, right? So if you find solutions for this one over here, it means that you have found solutions for this one, right? And it may not seem like a big deal, and you probably may just take it for granted, right? But this actually you can prove formally, right? We won't get into the formal proof. So that's the idea of theorem 1.15, right? Your row equivalent matrices, which is, for example, this one over here, this one over here. If you look at the corresponding systems, those corresponding systems, the system here and the system here, are equivalent. They have the same solution. Okay, alright, so let's take a next look at what we just did over here, right? So we have the system here. You form your augmented matrix, and now you did row operations here, right? And this over here is a systematic way of doing the row operations, which I didn't explain to you as yet, but we're going to look at now, right? And the point about this systematic way of doing your row operations is that really you want to get to something that is of triangular form. Right now, this isn't entirely complete over here. Eventually what we'll want to do is we want to get rid of this one over here, this two over here, and this two over here, right? Okay, so that actually is equivalent to doing a back substitution, right? So if you get rid of this over here, this over here, and this over here, you will no longer need to do the back substitution, assuming your solution is unique, right? Then once you do that, you will get the solution. Anyway, the point that I'm trying to make here is if you have your system and you form this augmented matrix, you want to know, well, what are you heading towards, right? What should I head towards, right? What should be the sort of matrix that I should be satisfied with as my stopping point, right? Okay, so let me see if I can get a next example of this. Right, okay, so here I have this system here, right? Okay, this is a system in 3 variables, 1, 2, 3 variables, and it has 4 equations in it, right? Okay, so you want to solve your system over here, right? So instead of doing equation operations, what we do is you form your augmented matrix here, right? Okay, your coefficients, right? Here, there's a 1 in front of this I0, so you have a 1 over here. Here you don't have any I0 variable here, right? So you'll have a 0 here, and so on, right? So this is your coefficients coming from your equations here, right? And your constants are on this side, right? Okay, so, and we're using something called Gauss-Jordan algorithm, but the point is you're going to do your operations in a systematic way until you come down to this matrix here, right? And this entire matrix here, this, well, it's a 4 by 4, right? Where you have, it's 4 by 3 on the side, and then 4 by 1 a vector on the side, right? Okay, but notice you start with this and you're applying your row operations until you get something of this sort of nice kind of triangular form, right? Right. Okay, so this over here is, once we see something like this, right, what we're going to realize is that this would be a stopping point, right? So we want to have an idea that you can't keep doing row operations until infinity, right? You need to stop at some point in time, right? Okay, so you stop when you get a matrix that is of a certain form, right? And that certain form is called for us is reduced row echelon form, right? RREF, right? So the next couple things that we're going to talk about is what is a reduced row echelon form matrix, right? Okay. All right, so a little bit of notation, right? If I have a matrix and it has a row just consisting of zeros, right, then you call it a zero, right? So that is sort of obvious, right? So this here, this is an example of a zero row over here, right? This fourth row of this matrix A, right? Okay, so likewise, this fourth row of this matrix here, that's a zero, right? Okay. If a matrix has at least one non-zero entry, then it's called a non-zero, right? Okay, so okay, so for example, this row over here, right? It has at least one entry, which is non-zero. Matter of fact, it has 3 of them, right? But the main thing is that you have at least one, right? So once you have at least one, right? Once you have something that is not zero in the row, right? Then it's a non-zero, right? So this matrix here has 3 non-zero rows, right? This one is a non-zero row. This is a non-zero, and this is a non-zero, right? If you look at this third row, right? I mean, you could say that this entry is 0 and this entry is 0, right? But that doesn't prevent it from being a non-zero, right? The main thing is that you have something that is non-zero in it, right? So either this one or this one will be good enough to tell you that it's non-zero. Okay. Right. Okay, now if you have a non-zero such as this third row over here, if you look at the leftmost non-zero number, right? Okay, so if you're looking at this third row and you're moving to the left, right? The furthest one to the left that is non-zero, which is this one over here, that's called a pivot or a leading coefficient, right? Okay, and you notice that, well, in this one over here, what I do is I circle the pivot, right? Okay, sometimes we will want the pivot to be equal to 1, but for this definition, all we need is that the leftmost non-zero entry is called a pivot, right? All right, okay, so a matrix is of row echelon form, so this is REF, right? You probably saw this RREF. So RREF is this REF that we're going to talk about now plus an extra condition, right? So if you want, anyway, so let's do REF first, right? Okay, so a matrix is REF in row echelon form if a zero row lies below all non-zero rows, right? So notice here that your zero row is below all the non-zero rows, right? Okay. Any pivot of a non-zero row has to be equal to 1, right? So if you're looking at, for example, this row over here and you look at the leftmost entry is this over here. And for it to be REF, right, it means that this over here has to be 1. And it's not hard to achieve that, right? Okay, so for example, over here, right, okay, so for example, over here for this row, right, this third row over here, right, notice your pivot here is 8, right? Okay, so here your third row, your pivot here is 8, right? And if you want to move towards getting it in REF form, right, what you need to do is you need to make that 1, right? And well, how do you make it 1? You just multiply by 1/8, right? Okay, and if you multiply by 1/8, this becomes 1 over here. And this is now 20 on 8, which is 5 on 2, right? Now, when you do that, you're not really changing information about the system, so you're allowed to do that, right? Okay, so if it is REF, what you want to do is you want to make sure that if you have a pivot, like this is a pivot over here, you want to make sure that you divide through so you get 1, right? So for a matrix to be REF, your pivots have to be equal to 1 over here, right? So for example, say this matrix here, this is not REF, right? Okay, this is not REF because this pivot over here is this pivot here is not equal to 1, right? Okay, so let's look at this third condition that you need for a matrix to be of row echelon form, right? Okay, so what they're doing here is, okay, first of all, what the overview what this means is that if you're looking at the pivots, right, so for example, this matrix here, the pivots are actually circled here, right? The pivots are going to come down in diagonal in this way. That's overall the diagonal is moving from left to right as you drop down, right? Okay, so you're coming down like this, right? That is roughly what this condition means, right? Okay, so something that does not satisfy this condition 3 is this over here, right? So these are the pivots, this one, 1, 2, and 3, right? And if you look at these pivots, you go from here to here, right? Which is okay, you go to the right, but then the pivot below it is to the left, right? And you don't want that, right? That is not good, right? If for example over here you have this pivot, the next pivot is on a row below it and it's to the right. And for this one, the next pivot is on the row below it, and it's to the right. Okay. This one over here, if you go, the next pivot is the row below it and to the right. That's okay, right? But going from here to here, this is bad, right? Because this pivot over here, if you go to the row below, right, in order for you to satisfy this third condition, the pivot needs to be to the right, which doesn't, it's to the left, right? Okay, so you want your pivots to come down in this going from left to right manner like this as you come down. You don't want it to zigzag around like this here, right? Okay, and you can put it formally like this, right? Okay, so you have, say, a one pivot in row I column J, right? So this is row in row I column J, and your second one located in row S column T, right? Okay. Right, so these are two pivots here, right? This one is in IJ position and this is in ST position, right? And what this condition is, it's saying that if S is bigger than I, right? So if you're looking at the pivot below, right, then the T must be bigger than J, right? In other words, the column index has to be bigger than this column index. In other words, it needs to be to the right, right? Okay, so this condition over here means that what you're doing is if you have your pivots here, you're looking at if the, okay, so if S is bigger than I, in other words, if the pivot is below, right, then the column the pivot is in, right, the column T needs to be bigger than this column over here, right? So the pivot needs to be in a column to the right. Okay. All right. Okay, on the other hand, this one over here, right, this violates, if you compare, say, these two, right, notice if you compare these two, you're okay, right, but if you compare these two, right, it violates this third condition, right, and you can check it. Okay, so far we talked about REF matrices, right, something in row echelon form. And now what we want to do is we want to consider what reduced row echelon form is, right? Okay, so something is in a matrix is in reduced row echelon form if it's already in row echelon form. In other words, if it satisfies these three conditions over here, right? And this last condition that, so three conditions from before, and then finally a fourth condition, is that the pivot of any non-zero row, right, is the only non-zero entry in the column, right? Okay, so for example, over here, right, this is a non-zero row, right, and this is your pivot, right? So non-zero row over here, and this is your pivot here, right? Okay, and that pivot has to be the only non-zero entry in the column, right? And if you look over here, that isn't true, right? Because if you're looking in this column here, right, this is not the only non-zero entry. This here is also a non-zero entry, right? So this does not satisfy this fourth condition over here, right? You have a pivot in a non-zero row, which is this non-zero row, that is, it is not the only non-zero entry in the column, and what's causing it violate the condition is this 4 over here, right? Right. Okay, now if on the other hand we consider, say, this matrix here, right, we look at this non-zero row and we look at this pivot here, right? Okay, this pivot, and we consider the column in which this pivot is in, right? And you notice in this column the only thing that is non-zero is this, right? So it's this 1, right? So in this non-zero row, the pivot is the only non-zero entry in the column. So this here satisfies this fourth condition, right? At least for this pivot. And notice also this one over here, this is a pivot, and it's the only non-zero entry in the column, right? Everything else is 0. And likewise for this pivot here, everything else is 0, right? Okay. So this you want to notice that this here, this is REF, right? This satisfies your three conditions over here, right? Any zero is below all, is on the bottom, right? Is below all non-zeros, right? Your pivots are all equal to 1, so you see in the three pivots over here, and this is circle, right? Notice this is not a pivot because this is not the leftmost entry, right? The leftmost entry in this row is this one, right? Okay, and your pivots are coming down as you drop from row to row, right? You move strictly from the left to the right, okay? So this satisfies these three conditions, but it doesn't satisfy your third condition over here. This is not for this column over here. This pivot is not the only non-zero entry, right? Okay, so this here, while it is REF, right, it is not RREF. Okay. On the other hand, this one here, right, this satisfies all three conditions, right? And if you look at the pivots, there's nothing else in okay, so if you look at this pivot, there's nothing else in the column. Look at this pivot, nothing else in the column. This pivot, nothing else in the column. So this actually satisfies these three conditions, which means it's REF, and it satisfies this additional condition over here for each of the pivots. So this is RREF, right? All right, and you want to notice that I actually can get this RREF from this one by multiplying this row here by -4 and add in, right? Okay, right. Okay, so if you have something that is REF, right, you can actually always make it into RREF by doing suitable row operations here, right? Okay, and this actually, in terms of solving equations, is essentially the same as doing back substitution, right? Okay, so once you get rid of everything else in the column for the pivot, right, effectively what you're doing is back substitution. Alright, so all of these definitions and so on with the REF and RREF, right, is all of it is really targeted towards solving a system of equations, right? So we saw this one already, right? So let's look at it again. We have this system of equations, four equations with three variables, right? Okay, so if we want to solve, we don't really need to carry around the variables, right? So we can just write the coefficients. So you form your augmented matrix, right? And now what you're going to do is you apply row operations, right? And you're going to apply row operations, and when you apply row operations, you're not changing the solution space, right? So you apply row operations, and the point about the row operations is you want to get something that is in the end is RREF, right? When you get something that is RREF, right, like this over here, right, then you can, from this RREF matrix, what RREF augmented matrix, you form a correspondence system, right? Okay, so this augmented matrix has this as its correspondence system, right? Okay, notice, for example, this third row over here, which is 0, 0, 8, 20, right? It's 0i0 plus 0i1, 0i2, sorry, 0i1, 0i0, 0i1, 8i2, right? And then 20 here, right? Okay, so this augmented matrix has this as a system, right? Now, this augmented matrix here, what you can do is you could form the correspondence system, right? And when you form the correspondence system, right, you're going to have I0 over here plus 0i1 plus 0i2 is equal to this constant, right? So all you get is I0 is equal to 2516. And when you have, this is going to correspond to the equation, this second row is going to correspond to the equation 0i0 plus 1i1 plus 0i2 is equal to 513, right? Remember the variables that we use in I1, I0, I1, and I2, right? Okay, so from the second row, I get I1 is equal to 513. And likewise, from the third row, I get I2 is equal to 512. So this is a system over here, right? But except the system is just so nice, really you could just read off the solution from this, right? This will not always happen, right? When you have a system, given a system, right? You won't always be able to get it down to this very nice form, right? This very nice form is when you have a unique solution, right? And you probably know that you have two other cases where you have no solution or a unique solution, or you have no solution or infinite number of solutions, right? Okay, so your three cases would be unique, right? Three cases would be unique, infinitely many solutions, and no solutions, right? Okay, right. Okay, so you have your system over here, you form your augmented matrix, and you're going to apply row operations until you get something that is RREF, right? And RREF is good because the corresponding system is usually of a very nice form, and you could figure out what your solutions are for this, right? And because your row equivalent matrices represent equivalent systems, it means that the solution of this is going to be the solution of this, right? Okay, so now we know what we're heading towards, right? If we start off with your augmented matrix over here, you're heading towards something that is RREF, right? Well, how do you actually get it, right? And how you actually get it is by using row reduction or the Gauss-Jordan algorithm, which you would have seen already in 1180, but I will review it over here, right? Okay, so the process for converting a matrix, such as say this one over here, into something that is RREF, right? Some matrix B that is RREF, which is, for example, this over here, right? That process is called Gauss-Jordan elimination. Okay. The Gauss-Jordan elimination, there's a formal algorithm over here, which is you can actually implement in code and so, right? And this will work, right? But it's hard to do this by hand where you're keeping track of the variables, right? So let me do an example and explain what the process is, right? Okay, so when you're doing row reduction or you're doing Gauss-Jordan elimination, this basically what you want to do is you do it column by column, right? Okay, so you start with this column, then you go to the next column, then you go to the next column, and if possible, you get to the final column, right? Okay, right. And when you go from one column to the next column, what you're going to do is you're going to drop by a row, right? And you'll see what I mean, right? And then once you go from this column to the next column, you're going to drop by a row again, right? That is essentially, that's something to bear in mind, right? So when you're doing Gauss-Jordan, you go in first column, so you work with your first column, then you start working on the second column. But when you start working on the second column, you drop a row, right? Okay, so you drop a row, right? So over here, you'll start with this guy and then you'll work on this column, right? And then you move across here, but now you're starting with something in this second row, right? And again, you work on this column, right? And then you go across on the third column and you drop a row again, right? So now you'll start with this one and work with that, right? Okay, so let's see how it works, right? Okay, so I have this matrix and I want to apply Gauss-Jordan, right? So the first thing is, okay, so you start with your first column, as I said, right? And with your first column, what you want to do is you want to locate in the first column, you want to make sure that this top entry over here is non-zero, right? If the top entry was 0, then what you'd need to do is you'd need to exchange, right? So an actual example of that is this over here, right? If you apply an Gauss-Jordan to this over here, and we start with this column, what you do is you look at this entry and you want to make sure that it is non-zero. And in this case, because it is 0, right, what you need to do is you need to swap, right? So you're going to swap row 1 and row 2. And when you swap row 1 and row 2, you're going to get this 1 over here coming up over there. And that's what you want, right? So you want to start when you your top left hand corner, you want to make sure that is non-zero, right? If, however, everything else in the row was 0, right? Sorry, everything else in the row. If, however, everything else in the column was 0, right? Then what that would mean is, well, you can't find anything to swap up with. And in that case, if everything else in the column is 0, then you just move on to the next column. And you start looking for something that is non-zero over here, right? Okay, but that's not the case over here, right? Over here, when we look at this first entry, the top left entry, that is non-zero, so we will work with that, right? And part of the Gauss-Jordan is what you're going to do is you're going to divide throughout by 2 because I want 1 over here, right? So this row, first row, I'm going to multiply by a half, right? So take my first row, multiply by half to get this 1, right? Why I want to do that is it's going to make my calculations down here a little simpler, right? Okay. Right, some folks may argue that dividing throughout by the 2 over here, right, may introduce some numerical error, and that's probably true, right? But for our purposes, we're just going to do it this way because really dealing with simple examples, and the cases that we will look at would be have a certain amount of numerical stability in them, right? Okay, right, so with this 2 over here, once you first locate something that's non-zero in this top left, right, then you're going to make this 1, right? Okay, so this is actually going to be a first pivot, right? And what you want to do is with this pivot over here, you want to make everything else in the column 0, right? So I want to make this 0 and I want to make this 0, and I'm going to do it via row operations. Okay, so, well, how do you make this 0? What you do is you multiply this row by minus 2 and you add it to the second row, right? Okay, so it's minus 2 times row 1, right, plus row 2, right? So you're multiplying this row by minus 2 and adding it to this. And that would give me the 0 over here plus other stuff, right? Notice what I have up here will affect the second row here, right? Okay, so for example, the minus 2 times the minus 1 would give me 2, and then the 2 plus 1 would give me the 3. Right? Okay, so I eliminated this by a row operation. I made this 2 over here converted to 0, right? And then I do a next row operation that would convert this 1 over here to 0, right? So how would I do that? I'd multiply this row over here by minus 1 and add it to this row, right? So minus 1 row 1 plus the row 3, right? Okay, so multiply over here by minus 1 and add it to this, right? You're going to get minus 1 times this 1 and you add to this 1 over here, so you get a 0, right? Minus 1 times minus 1 would give me 1 plus this 1 would give me the 2 and so on, right? So what I'll get is I'll get this third row over here where I have zeros, right? So first thing, okay, so to recap, first you look for a non-zero entry in your top left, right? You divide throughout to make it 1, and then what you're going to do is you're going to make everything else in that column 0, right? And now you're actually done with that column, right? And now that you're done with this column, as I said, you're going to move across to the next column, right? And when you move across to the next column, you're going to drop 1 row over here, right? So you're not going to start working with this one here. You're going to start working with this one, right? And when you're working with this one, you're actually going to be doing something similar to what you did before, right? So you're looking at this tree over here, and the first thing we want to do is you want to make it 1, right? So in order to make this tree 1, right, you need to use a row operation that will convert the row so that this tree becomes 1. In other words, you're going to multiply this row by 1/3, which is this over here, and you get this, right? So you get your 1 over here, you got a minus 1 here, and you got a 2 there, right? And now that you have this pivot over here being equal to 1, what you want to do is you want to make everything else in the column equal to 0, right? Below and on top, right? So doing on top is, as I said, sort of like doing back substitution, but you don't need to think about it. All you need to do is really for this here, you make this 0 and make this 0, right? It's sort of nicer to make the one over here 0 first and then make this one 0, but in fact it makes no difference, right? Okay, so with this pivot over here, I want to make this entry 0, so I multiply throughout by -2 and add to this, right? So -2 times row 2 plus the row 3 gives me, when I add it to the, so -2 times row 2, when I add to row 3, will in fact just give me zeros over here, right? So you can check mine. -2 times 1 is -2 plus this 2 over here gives me 0, right? -1 times -2 would give me 2 plus the 2 -2 would give me 0. -2 times 2 gives me -4 plus the 4 over here gives me 0, right? Okay, so this row over here will just give me, is just going to be zeros here, right? And you want to notice that actually if you look at this row here and you look at this row and you multiply this row throughout by 2, you'd in fact get this row, right? So this row is a multiple of this one, right? And because this row is a multiple of this one, when you do your row operation, when you do this type of row operation with eliminating, right, the entire row will come out, right? That is only if this row over here is in fact a multiple of this one, right? Okay, so now I have this pivot over here and everything else in the column is non-zero, right? And now what I'm going to do is I move across to the third column, right? Now when I move across to the third column, okay, so there's a couple of ways to realize that you stop. I'll do it this way and I'll explain the next way in a second, right? Okay, so you have this pivot over here, you're done with this column, and now you move across here. Now when you move across to the third column, you need to look for a non-zero entry here, right? But this is 0, right? So you can't use this. Now, if you're going to swap with something, you need to swap with something below, right? But there's nothing to swap with, right? So you can't do anything over here. According to the algorithm, right, what you would do is you'd have to jump across again, right? But you can't actually jump across again. If you go across in the fourth column, right, you can't drop into a row over here, right? So at this point you would stop, right? Okay, so that's the idea over there, but the next way to realize that you're going to stop is once you hit a row of zeros over here and everything else actually below is just zeros, right? Okay, so if below this non-zero all your rows are 0, then you really can't do anything else, right? You're gonna stop there, right? And when you stop, if you decide to stop here, it's always a good idea to check to see if this where you stop is RREF, right? Because that is where you're supposed to stop, right? The algorithm is supposed to stop at an RREF, right? And that actually is a unique answer, right? Okay, so does this satisfy my 4 conditions for RREF, right? The 0 row is below all non-zeros. Yes, that's true, right? The pivots are equal to 1. Yeah, these are 2 pivots there and they're equal to 1, right? Are your pivots coming down from left to right as you drop from one row to the next row? Correct, yes, this one, right? And is it in reduced row echelon form, meaning that the pivots are the only non-zero entries in the column? And yes, that is the case, right? Okay, so this satisfies all 4 conditions, and once you get an RREF, you can actually stop there, right? Okay. Usually you just check with the algorithm. You know when to stop when you just have hit like a 0 rows, right on the bottom, right? But the next way to check to see that you should stop is you check to see that this matrix is RREF, right? Okay, so this is an example of using a Gauss-Jordan algorithm, right? You start with your matrix over here, and when you apply row operations, you come down to something that is RREF, right? Okay, so let's say look at this example again and see if we could put everything together, right? All right, so I want to solve the system here, right? So if you're going to solve the system, how you're going to do it is you first form your augmented matrix, right? So you get your coefficients from your variables over here, you put it on the left hand side of this vertical line, and you put your constants here on this right hand side, right? Okay, and now what you're doing is you apply your Gauss-Jordan algorithm, right? So you look for your non-zero entry in the top left, and you see it over here, right? And there is there's nothing to do really actually in this first column here, right? Okay, so what happened over here for this Gauss-Jordan is you move to your second column, right? Move to your second column and you look at the row below, right? So you look at this 12, right? So you're going to be using this as your pivot. You first want to make it into 1, right? So what you do is you divide throughout by 12, right? So row 2 by 112, right? Okay, and then what you do is you use this pivot over here to make this equal to 0, and you make this equal to 0, right? Okay, so that is, notice going from here to here, right? What happened is that this entry now became 0, right? After this row operation, right? And going from here to here, right? This entry over here in the second column became 0, right? After doing this row operation, so you get this, right? And now you're done with this column over here, right? This pivot is the only non-zero entry in this column, so you need to move across, right? You move across, right? You move across to the next column, and then you drop one row, and so you're looking at this. It is non-zero, so that's good. So you're going to be working with this. You divide throughout by 8 to make it 1, so you get the 1 on 5 on 2. And what you want to do is with this 1 over here, right? What you want to do is you're going to make everything else in the column 0, right? So you do a row operation that makes this 0, right? Okay, so you add this row here to this row, right? So row 3 plus row 1. Okay, you got a 0 over here, and you got a 25 on 6. And then you also want to make this 8 over here 0 by a row operation. Okay, so minus 8 times this row, minus 8 times row 3 plus row 4, and that gives you a 0 over here, right? And in fact gives you a 0 here and a 0 here, right? Okay, so from this and later on we will see that this system is how it's the fact that you don't have your pivot in this last row over here means that the system is consistent, but we'll talk about that in the next lecture. But for the time being, what I have is I have this augmented matrix, and that corresponds to this system. Okay, and once you write down your system, you notice it is extremely easy to just get the solution. The solution is just simply I0 is 2516, I1 is 513, I2 is equal to 512. Okay, so this system here has a unique solution, which means that the one that you started with which is by the theory equivalent, it has the same solution. So the solution for this original system is just this answer over here, right? Okay, so that's how we're going to go about solving systems, right? You have your system to start off with, form your augmented matrix, apply Gauss-Jordan until you get an RREF. From the RREF, you look at the associated system, and then the answer set, the solution set from this is going to be the solution set of your original system.